In this example, we're going to get a picture for what the definition for the limit of a sequence means. So the sequence we're going to take a look at is 2 minus 1 over root n. We claim that the limit of that sequence is 2. And I'm going to write out the first few terms just to get a sense for how the sequence is behaving. So if n is 1, I would get 2 minus 1 over the square root of 1. So that's 1. If n is 2, I would have 2, 1 over root 2. That's, well, let's get a calculator to do calculations like this for us, even though we could get kind of close. So minus 1 over root 2. All right, so that's about 1.29. And then if n is 3, we have 2 minus 1 over root 3. And that's about 1.42. And if n is 4, we have 2 minus 1 over the square root of 4. That's 1.5. And then if n is 5, 2 minus 1 over square root 5. Well, let's see what that gives us. And that's about 1.55. So the first few terms of the sequence look like 1, 1, and then 2 about 1.29, 3 about 1.42, 4 is 1.5, 5 a little bigger. So it looks like we're sort of going up and bending a little bit. So those are the first few terms of the sequence, and we can kind of see that as we move along, we're going to be kind of rising up towards L equals 2. All right, but we want to kind of see how we could apply the definition to this sequence. All right, so let's consider the same thing we always start with, a sub n minus L. Our proposed limit is 2, so 2 minus 1 over root n minus 2, that's minus 1 over root n. And so when I take the absolute values, I get 1 over root n. And that's what I want to make small. Right? I want that less than epsilon. And to make that happen, I would need to take any natural number that's strictly bigger than 1 over epsilon squared. So my capital N is anything bigger than 1 over epsilon squared. All right, so let's see what happens if, for example, we took an epsilon equal to 0.5. How far would we have to go out in the sequence to guarantee that the sequence members are within 0.5 of the target limit 2? So geometrically, what that means is we put what we call an epsilon band around the target limit 2. So at 2.5 and 1.5, those represent points that are 0.5 below 2 and 0.5 above 2. And our epsilon band looks like this. So we've got epsilon is 0.5, epsilon is 0.5, and we need to figure out when do we get inside that band. Well, in our few examples we did, when n is 4, we get 1.5. So that point should have been right there, and then the 5 was a little bit higher, 1.55. So because of the strict inequality for epsilon, n equals 4 doesn't quite do it, right? It's equal to 1.5. N equals 5 does do it. It's all the way inside the epsilon band. So in that case, when epsilon is 0.5, 1 over epsilon squared, that's equal to 4. So the first capital N that works would be anything bigger than or equal to 5. And as long as we're past 5, right, we stay inside that epsilon band. All right, now let's try a smaller epsilon band. All right, so we have to show that the definition holds not just for 0.5, but for any positive number. So what happens if epsilon is equal to 0.2? Then 1 over epsilon squared, what is that? 1/5, 5, so this is going to be 25. So what this is saying is that our n needs to be bigger than or equal to 26. All right, so here's an epsilon band of 0.2 roughly. All right, so we're inside the last one. And what we would see, right, it's kind of hard to keep all of these points in exactly the right spot, but what we would see is that if n is equal to 25 over here, then the sequence would be 1 over root 25, which would be 1.8, and that is right on the band, and then we would be in it and would stay in it. So in order to qualify as the limit, we have to be able to play this game no matter what the epsilon is. So if epsilon was 0.01, then 1 over 0.01 would be 100, and 100 squared would be 10,000. So we would have to go out to the 10,000th term. But once we were there, all of the terms in the sequence would be within 0.01 of the proposed limit. And the work that we did guarantees that that always works because, right, we didn't pick a specific epsilon here. We solved the problem for any epsilon that's a positive number. All right, so with apologies for the artwork, I hope this gives some understanding of the geometry behind the definition. And of course, like any of the videos, I'm happy to answer questions in class.